Alright, so today's lecture is going to introduce you to geospatial data models. So a geospatial data model is a formal means of representing spatially referenced information. It's a simplified view of physical entities and a conceptualization of reality. What I mean by simplified conceptualization of reality is that while we would like to store a complete model of reality, we really can't do that as it's not possible to represent every possible variable that exists in reality. For instance, if we want to represent a road in a geospatial data model, we would probably store the pavement type, number of lanes, and speed limit. We would not be able to store the amount of wear on the road based on friction with all of the tires that have traveled the road, nor would we necessarily want to. For our conceptualization of reality, we only want to store the information that is important for our task. A geospatial data model is composed of two parts, objects and attributes. The object and attributes are combined together to form a simplified concept of reality. The object stores the geometry of the spatial phenomena that we are modeling, and the attribute stores the descriptive information related to the object part of the geospatial data model. As an example, here's a satellite view of the lower 48 states of the United States of America. Let's assume that this satellite picture represents reality. So the question is, how can we simplify and conceptualize this picture of reality for our purpose? What if we want to conceptualize the USA as a basic reference map that only shows the boundary of the United States of America, its individual state boundaries, water features, and major roads? We're going to represent our chosen model of reality using a geospatial data model. Once we have the data in the geospatial data models, we are then going to apply some good map design principles to arrive at a map that looks like what we would expect. This is a general reference map of the United States of America. What we see on this map is our simplified view of reality. We see the national outline, state outlines, water features, roads, and even elevation information. Note that while we are representing roads, we choose only to represent major roads, and are leaving off all of the other roads for the purpose of readability. By only showing major roads, we have simplified reality for our purposes. In fact, every facet of reality that we are displaying on this map has been simplified in at least one way. Now, if we're going to simplify reality and talk about how we do that, we're going to store the concept of reality in a geospatial data model. We need to understand the way in which spatial phenomena are structured. There are two types of spatial phenomena that we are going to discuss, discrete and continuous. A discrete spatial phenomena is anything that exists that is individually distinguishable. It has well-defined boundaries, and it is easy to see where it begins and ends. It does not exist between where we observe it to be. For example, a stream or lake is very easy to tell where they begin and end, and they are easily distinguishable individually on the Earth. The same thing goes for roads. Roads have well-defined boundaries and are each easily distinguishable as individual roads. The second type of spatial phenomena is continuous. A continuous spatial phenomena is something that exists between our observations. It is data of a continuous nature that cannot be isolated as an individual. It is perhaps best explained through examples. For instance, temperature is a continuous phenomenon that gently varies throughout space. A temperature reading at a single location does not represent a well-defined location where it is exactly that temperature. Instead, the temperature reading must be put in the context of the surrounding area as part of the larger surface of temperature readings. Temperature should be considered as part of a larger continuous spatial phenomena. Elevation is another example of a continuous spatial phenomena. An elevation reading is only a single point as part of a larger surface. So if we consider our continuous and discrete spatial phenomena, we could simplify them to a map that looks like this. We would consider this map to be a reasonable representation of the United States of America and the spatial phenomena that falls within. The discrete spatial phenomena would be the roads, the national boundary, the state boundary, and the water features. The continuous spatial phenomena would be the elevation information on this map. Now that we know that we could store representations of discrete and continuous spatial phenomena in geospatial data models, we should consider how we organize them. Typically, spatial phenomena are organized into separate geospatial data models by theme. Separating our models of reality will provide us with many benefits when it comes to querying and analysis. Additionally, we tend to group things that are similar together in our minds, so we mirror that tendency in our geospatial data models. In the example on the screen, we have modeled 5 facets of Mexico City. We have cities as our top layer, water features, roads, state boundaries, and then at the base, our national boundary. While we do separate the spatial phenomena into separate geospatial data models in the computer, if we lay these layers on top of each other and flatten them, we can then produce a map that looks like this. This map is composed of 5 geospatial data models, one for each theme of information that we have modeled from reality. By placing these layers on top of each other, we can produce useful visualizations, conduct analysis, and execute queries. And alas, we have represented reality using both objects and attributes. But let's talk a little bit more about attributes. So, attributes are the non-spatial characteristic that describe spatial entities. Attributes are commonly arranged in tables where a row is equivalent to one entity and a column is equivalent to one attribute or descriptor of that entity. Typically, each row relates to a single object and a spatial data model. Also, each object will have multiple attributes that describe the object, in most cases. All attributes are often displayed in a table format on the computer. It can be stored in many ways, such as a flat file format or in a database management system. Let's look at an example. Let's say we have a spatial data model that stores the location of fire hydrants. For each fire hydrant to represent the object, we would store the position. In addition to the positional information, we will also store attributes that will describe those fire hydrants. In this example, we are storing color, service date, and flow as 3 attributes that describe what this particular fire hydrant at this particular position on Earth is. The position, color, service date, and flow will be stored as one row in an attribute table that will contain 4 columns because there are 4 descriptors for this fire hydrant. Attributes can store all kinds of different descriptive information. However, depending on the descriptive information stored in each attribute, some properties are implied. So operations are permitted, and other operations and properties are not allowed and not applied respectively. We could break attributes down into 4 categories: nominal, ordinal, interval, and ratio. The first attribute category is the nominal attribute category. A nominal attribute provides descriptive information about the object such as the color of the object, the name of an object, so for instance a city name, or the type of an object. What's more important here is that this descriptive information does not imply any order, size, or any other quantitative information. That means that you cannot state that one attribute is greater than or less than another attribute, or you cannot multiply attributes together. So for instance, it does not make sense to multiply the color blue by the color red. The only comparisons you can do with nominal attributes are to check whether the attributes are equal or not equal to each other. In addition to text descriptions, the nominal attribute category includes descriptive information such as images, movies, and sounds. The next attribute category is the ordinal attribute category. Ordinal attributes imply a ranking or order based on their values. These values can be descriptive text or numerical. For example, I can describe an object as having a high, medium, or low ranking, or a ranking of 100, 50, or 1. In either case, these ordinal attributes allow us to specify rank only and not scale. So for instance, we can state that high is ordered higher than low, and high is ordered higher than medium, and low is ordered lower than high. But we cannot say that high is twice as high as medium, or that medium is twice as high as low. Additionally, if the numerical attributes are of the ordinal attribute category, again, we can say that 50 is ordered higher than 20, and 20 is ordered higher than 10, but we cannot say that 50 is twice as high as 25, or that 25 is twice as high as 12 and a half. Even though we're using numbers to describe rank, do not let that confuse you into thinking that a scale is implied. The third entry category is the interval attribute category. Interval attributes imply a rank order in magnitude or scale. Interval attributes use numbers. However, those numbers do not have a natural zero, and they use an arbitrary 0 point instead. For instance, if we look at temperature on the Fahrenheit scale, 0 degrees Fahrenheit is not a natural 0 point for temperature. It is a human-defined 0 point. Therefore, while we can say that 50 degrees Fahrenheit is 10 degrees Fahrenheit more than 40 degrees Fahrenheit, we cannot say that 50 degrees Fahrenheit is twice as hot as 25 degrees Fahrenheit. Again, because 0 degrees Fahrenheit is a human-created zero and not a natural phenomenon. With an interval attribute, addition and subtraction do make sense, but not multiplication, since values are relative from an arbitrary zero. The fourth and final category is the ratio attribute category. A ratio attribute implies both rank and order, and magnitude about a natural zero. The ratio at, The ratio at the category uses numerical, sorry, got something in my chest. The ratio attribute category uses numerical attributes and addition, subtraction, multiplication, and division, as the values are absolute from a natural zero. So for example, if we are measuring speed in miles per hour, an item at rest is at a natural 0 miles per hour and is not moving. Therefore, not only can we state at 50 miles per hour is twice as fast as 25 miles per hour, we can also say that it is greater than 25 miles per hour. Therefore, we're applying both rank and magnitude. Now you know 4 different attribute categories. Let us take a look at an example dataset and its related attribute table, and try to identify each column as holding nominal, ordinal, interval, or ratio data. The dataset we are looking at contains 4 objects, and each one of those objects represents a tree. Each object has 4 attributes showing in the attribute table: ID, height and feet, type, and class. Let's start with the height attribute. If we think about height, it is a natural phenomenon that has a natural 0 point, 0 feet. Therefore, as we know we are modeling height, and heights have a natural 0 point, we can infer that the height attribute contains attributes of the ratio category. Now let's look at type. The type attribute contains a description of the type of tree. Since these attributes do not use numbers, we can immediately remove interval and ratio from the list of possibilities. That leaves nominal and ordinal. We think about what type represents. It is a description of the type of tree, but the question becomes, is there any rank implied when we describe the type of tree? The answer is no. We cannot state that a pine tree is greater than or less than a mesquite tree. All we can compare is whether a pine tree is equal to or not equal to a mesquite tree. Therefore, the type attribute holds nominal attributes. Moving to the class attribute, it represents a relative measure of the height of the tree. Again, as we are not seeing numbers in this attribute column, we can rule out interval and ratio attribute categories. This leaves nominal and ordinal. Let's first consider ordinal for this attribute column. Logically, we can order tall, medium, and small. So we can state that a tall tree is greater than a medium, and a medium is greater than a small, and a small is less than tall. Therefore, this data represents ordinal information. Last, let's look at the ID field. In this case, the ID was automatically generated by the GPS unit used to record the location of the trees. It does not represent any meaningful measure of the tree other than to differentiate one tree from another. Note that the ID is a number. Since it is a number, that is this does not rule out any of the four attribute categories, as all four attribute categories can hold numbers. Therefore, we need to think about, what does an ID mean? Let's think about a driver's license number. Your driver's license number is a number that uniquely identifies you as a driver in that state, for instance. Would it be logical for me to ask you to multiply your driver's license number by my driver's license number? No, as that would not produce any meaningful results. Here's another question. Is it meaningful for me to state that my driver's license number is greater and better than your driver's license number? No. It only makes sense to state that my driver's license number is different than your driver's license number because we are different drivers. Therefore, if we cannot do multiplication, subtraction, addition, or rank dividers, our driver's license numbers, and that just leaves us with the nominal attribute category. In the case of our trees dataset, the ID is analogous to the driver's license number, even though it is a number. It is simply a unique identifier that we use to separate trees from each other, just as we would separate individual drivers using a driver's license number. So let's finish talking about attributes real quick. So computers fundamentally think differently than humans. While humans see numbers, letters, pictures, and sounds, a computer only sees zeros and ones, or binary data. Therefore, we need a way to translate the numbers, sounds, and videos as humans know it to a form in which a computer can understand and store that information. Therefore, computer scientists have created data structures that can be used by us to translate our information into a format which the computer can store in its memory. This data structure is known as data type. There are four typical data types that we use in GIS: integer, float real, text string, and date. It's important that we specify which data type we are going to use to store information in the computer's memory, so that we may use the computer's memory in the most efficient manner. And let the computer know which operations are allowed for each data point stored in that memory location using that data type. So the first data type is the integer. An integer is a whole number, such as the number 1, number 2458, and the number -54. Integers can be used for mathematical calculations. However, any resulting fraction of a whole number will be rounded or truncated. The float, or real data type, holds a decimal number, such as the number 1.452, the number 254,783.1, or the number -845.157. Like the integers data type, the float or real data type can be used for mathematical calculations. No rounding or truncation will take place when using float or real numbers, depending on the number of significant digits you specify. The text or string data types contains characters such as the character A, the characters GIS, or the characters 125 Main Street, or the number 9. Even though text may contain numbers, it is important to note that they cannot be used for mathematical calculations. However, strings can be manipulated to find substrings or to cut strings and locations. The last common data type is date. The date data type holds time and date information, such as 12/10/2010, or 10/12/10, or December 10th, 2010. The date data type cannot be used for mathematical calculations, however. It can be used to determine and calculate lengths of time between two different dates or times. Additionally, the computer stores the date information in its own internal data structure, but it can be formatted to output the date in many different ways, as shown in these examples. All right, for this section, we're going to discuss 3 spatial data models available to us in GIS. There are 3 common spatial data models being used in GIS today: vector, raster, and triangulated irregular networks. This section will describe the vector data model first. A vector data model defines discrete objects. Examples of discrete objects are fire hydrants, roads, ponds, or cadastral. A vector data model is broken down into 3 basic types: points, lines, and polygons. All 3 of these types of vector data are composed of coordinates and attributes. A point uses a single coordinate pair to define its location. Points are considered to have no dimension, even though they may have a real-world dimension. For the purpose of a GIS, no dimension is assumed. Each point has associated attribute information, and the information is attached to the center of the point. Examples of spatial phenomena that would be modeled well as points are light poles, manhole covers, and crime locations. What you see on this screen are the different ways to represent airports using a point vector type. Even though the symbols are different, they all represent airports, and all of the attributes for each airport are linked to the center of each one of these symbols. A line vector type is defined by an ordered set of coordinates. Each line and curve is made up of multiple line segments. However, occasionally curved lines are represented mathematically. There are 2 words that we need to define when discussing lines: the node and the vertex. A node is where a line begins or ends. A vertex is where a line changes direction. The smallest possible line will have 2 nodes, a start node and an end node. Longer lines will have at least 2 nodes and many vertices in between where the line changes directions. Attributes may be attached to the entire line, individual nodes, or individual vertices. Therefore, each line may represent multiple rows of attributes in the attribute table. For example, if a line represents a road, each road segment between 2 intersections may have its own address information, such as the start address and the end address for that block. An intersection may have an attribute that describes where the intersection has a stop sign or stoplight. The other option is for the entire line to have one row of attributes, no matter how complex the line. Examples of spatial phenomena that are modeled well by lines are roads, pipelines, outlines of objects, and power lines. This graphic shows a stream network represented by the line vector type. This graphic shows a stream network represented by the line vector type. Sorry, I said that twice, but I didn't show it to you the first time, so hey, here it is now. Woo! All right, on to the next one. The last vector data type is the polygon. A polygon is formed by a set of connected lines where the start and end endpoint have the same coordinate. As the start and end points have the same coordinate, the polygon will close and it will have an interior region. Attribute information is attached to the center of the polygon, no matter how complex the polygon. Examples of spatial phenomena modeled well by polygons are lakes, cities, trees, and political boundaries. Here's an example of 5 US states represented as individual polygons. The raster data model best represents continuous objects such as temperature or elevation. A raster is a regular set of cells or pixels in the case of a photograph, and a grid pattern, also referred to as a matrix. Okay, sorry about that. Each cell in the raster contains a single value, and the coordinate of each cell of the raster refers to the center of the cell. Therefore, the single value stored in each cell of the raster applies to the entire cell in the raster matrix. Each cell can be defined by a cell dimension, such as the cell width and height. Often, cells are in a raster or square, so the cell within cell height will be the same. This is an example of a raster. In this case, the raster is an aerial photograph showing a portion of the port of Corpus Christi, Texas. Photographs are the most common data sets that are represented by rasters. In fact, the photos that you take with your camera or camera phone are stored in raster format. So for instance, a JPEG is a raster file stored in the JPEG format. In these pictures, each cell contains a single value that represents the color reflected from the objects. In GIS, it is important that we know the resolution of the raster. The raster resolution is the cell size of each cell of the raster. Unlike how photographers represent resolution as the number of megapixels their camera uses, in GIS, we are not as concerned about the number of cells, but how much area on the ground each cell covers. There's a direct trade-off between resolution and file size. The cell coordinates is a center of the point cell, and the coordinate applies to the entire cell area. Again, it is important to reiterate that each raster cell represents a given area and the value assigned applies to the entire cell area. If there is more than one value that could fall inside the raster cell, then the raster cell may contain the average, central, most common, or other value covered by the cell. For instance, let's revisit the picture of the Port of Corpus Christi, Texas. If we zoom into the ship, we will be able to see each individual cell. You can now clearly see that each cell only contains a single color. Here zoomed into the raster, you can see that the resolution is not infinite, and each cell covers a large location on the ground. Additionally, we know that each cell can only contain a single value, but on the ground, multiple colors were reflected. So in this case, the camera have the choice of taking the average color, most common color, or a single color for the cell. When this happens, data is lost through aggregation, and it is important to keep that limitation in mind. While we would like to have a much higher resolution photo of the ship, this would be practically expensive and would produce an outrageously large file size. So the trade-off was coverage of a larger area, but at a lower resolution. In addition to colors, a raster can store other data values. For instance, this raster contains a single character in each cell, where each character represents grass, road, or water. Again, we can guess that each cell doesn't contain exactly a water, a road, or grass. So we assume that some aggregation has taken place. But in either case, the raster can store information about the continuous phenomena, in this case, land cover, in a meaningful way. If we apply colors to the previous grass, road, and water values, we can visualize the data with something similar like this. This visualization shows what it is covering the Earth in each cell of the raster and allows us to simplify our vision of reality to see spatial patterns. So here we have one last look at differences between rasters and vectors. So we know that rasters are good for frequent changes. They provide us simple data models, easy overlays, and they're best for things like digital imagery. While vectors, they have compact data storage. They're great for network and linear features. Humans tend to be more familiar with vector data because we don't live in an 8-bit world. And vector data can also contain topology. So let's start talking about tins. A triangulated irregular network, most commonly referred to as a tin, is a network of triangles connected together to create a three-dimensional surface, where the triangles in the network are not crossing. Triangulated irregular networks are more complex than rasters. However, they are more efficient space-wise. Additionally, triangular irregular networks can easily accommodate different sampling densities, where rasters cannot. Lastly, triangulated irregular networks preserve each input measured point, again, where rasters cannot do that. If we look at the anatomy of a tin, it's composed of points, edges, and faces. A point represents an input data value that is preserved and defines an endpoint for a triangle. The edge is the line drawn between each point, which creates the outline of the triangles. The face is the area or surface inside each of the triangles. Triangulated irregular networks can be quite large and look quite complex. However, if you think about what each point of the triangle represents, in this case, an elevation point, and you know that the faces are the flat faces of a triangle, you can decipher some of the features in a 10 without seeing it colorized. For instance, the very large triangles in the top corner of this are trying to, in the top left corner of this triangulated irregular network represent a lake behind a dam. The very dense triangles flowing from the bottom of the triangulated irregular network to the bottom right of the triangular irregular network represent a river. Ugh, tongue twisters, right? When we apply colors to this triangulated irregular network, based on the elevation value, it becomes clearer what the triangulated irregular network is representing. It is representing the continuous spatial phenomena known as elevation. And in this particular case, it shows a lake behind a dam and the surrounding terrain, and a river that's leading away from the dam. All right, that concludes our discussion on geospatial data models. All right, if you have any questions, feel free to email me or leave them in the comments. All right, thank you. Have a good one.